The computers being used today are said to reach the limits of Moore's law as early as 2025, in which the growth of computing power will reach a plateau. Meanwhile, our society is facing numerous problems that cannot be solved even with the latest supercomputers, and it is vital to have a computer that can deliver a much higher performance. Fujitsu Laboratories is taking on the challenge to develop quantum computers, the next revolution in computing. Classical computers, in principle, use a bit that represents a single value of either 0 or 1. However, quantum computers use a qubit that represents both 0 and 1 simultaneously. This is a conceptual diagram of a qubit. When the arrow is pointing up, it represents 0. And when it's pointing down, it represents 1. However, a qubit can be in a state where the arrow is pointing in a tilted direction. When it is measured in such a state, 0 is observed 80% of the time, and 1 is observed 20% of the time. In this state, 0 is observed 30%, and 1 is observed 70% of the time. As seen here, the 0 and 1 in qubits are superposed. Thus, as the number of qubits increases, the amount of information that can be processed increases exponentially, compared to classical bits. If you have 2 qubits, the square of 2 is 4. Therefore, it can process 4 times the information. With 4 qubits, 2 to the 4th power is 16. That's 16 times. 10 qubits is about 1,000 times, and 30 qubits can handle roughly 1 billion times the amount of information. Furthermore, qubits also have wave-like properties. Utilizing the wave interference phenomenon allows us to arrive at the answers. If 100 qubit or 1,000 qubit computers could be created, they are said to be able to solve complex problems that are beyond the capabilities of a classical computer. In order to make qubits a reality, various methods are being proposed for the quantum gates. Superconducting qubits use cryogenic superconducting circuits. Diamond spin qubits use impurities created inside a diamond. There are other methods, such as silicon qubits and trapped ion qubits. Researchers at Fujitsu Laboratories are investigating every method for such hardware. In particular, we are carrying out joint research on superconducting qubits with Professor Yasunobu Nakamura of both RIKEN and the University of Tokyo. We are also working with Delft University of Technology in the Netherlands on the diamond spin qubit. On the flip side, errors are inevitable based on the principles of quantum computation. One of the key points for development is knowing how to prevent errors. The notation of quantum calculations looks similar to musical notes dancing on staff lines, where moving qubits are represented on a diagram called a quantum circuit. The vertical lines and squares on the so-called staff indicate the operations qubits have on other qubits, and we arrive at the answer through such operations. When using qubits, however, the amount of error increases with longer calculation time. With first-generation quantum computers scalable to 100 qubits, NISQ, it is planned for the calculations to be completed within its coherence time, which is the time duration before an error occurs. Taking this into account, the computing time given using superconducting qubits is merely 0.1 milliseconds. That's why we let quantum computers calculate the parts that exceed the capabilities of current computers, and let the classical computers do the rest. This combination allows us to arrive at the answers. In the future, we plan to add error correction technology that would allow longer calculation time. Specifically, what we now consider as one qubit will each be replaced with a number of qubits, such as 100 or 1000 qubits. Even if an error does occur in one of them, it can be corrected by comparing it with the rest of the qubits. In order to develop such platform software, Fujitsu Laboratories is conducting joint research with Quantum Benchmark, University of Waterloo in Canada, and Osaka University. At Fujitsu Laboratories, we focus not only on hardware and platform software, but we are also putting our efforts in developing algorithms and applications. As competition intensifies, it's hard to tell how quantum computers will evolve. That's why Fujitsu Laboratories is exploring the possibilities at every layer. Furthermore, our research team hopes to swiftly put quantum computers into practical use while making the most out of classical computers. By doing so, we would be able to perform calculations for quantum chemistry and complex systems that have been considered impossible until now. We will continue to take on the challenge of finding solutions for difficult social problems, promoting digital transformation in society.
Fujitsu, shaping tomorrow with you.